Hey guys, sometimes we take things for granted. Take for example this lens arrangement shown right here. I got two lenses, one positive powered, one negative powered, separated by a distance given by the difference between their focal lengths. To a lens designer, this arrangement produces magnifying power. In fact, it's a telescope arrangement called the Galilean Telescope. But to everyone else, it's not obvious why this should produce magnifying power, right? So let's try to improve the situation a little bit by providing the missing information, which is rays from the edge of the scene. For example, let's say I'm looking at a mountain, a very distant mountain. The bottom of the mountain represents eye level. So rays from the bottom of the mountain are like these blue rays right here. Rays from the top of the mountain are like these red rays right here. And they subtend an angle theta at the front right here. And since you and the telescope are very far from the mountain, then essentially speaking, or practically speaking, the same theta is subtended at your eye without the telescope, producing an image of the mountain with a height h, shown right here in your eye, right? Now, what happens with the telescope is that if you put the telescope in front of your eye, the rays coming out from the telescope has an angle theta prime that's bigger, all right? It's bigger, producing an image in your eye that is larger at height h prime. And the ratio h prime divided by h is the magnifying power. Now, if you apply the mathematics, which are also not obvious because you also got to know that there's something called a thin lens equation. 1 over focal length equals to 1 over object distance plus 1 over image distance. You can't apply that unless you keep trying and doing exercises. But if you do that, and notice that the second lens forms an image of the first lens right here at distance d prime, and if you apply that thin lens equation, put it into the mathematics, what you'll find is that the magnification is given by f1 divided by f2, the ratio of their focal lengths, right? And if you go back to the first slide, if you extend the blue ray further down until it intersects the optical axis, that length is f1, the focal length of the first lens. And f2 is the length given by this lens here to the point at which this extension intersects the optical axis. That ratio by geometry is also equal to the ratio of this diameter to this diameter, and that gives you magnifying power, right? So you can pause this scene here to check the mathematics yourself and see that that's true, and hopefully that helps. Thank you for your time. Bye-bye.